The secondary current I2, which is determined by characteristics of the load. This is secondary current creates a self-induced EMF, self-induced secondary magnetic flux field pi 2 in the transformer core, which flows the exact opposite direction to the main primary field pi 1. Understood? I'm already explained. The flux 1 pi 1 because of primary side, flux pi 2 is because of load. Okay, flux pi 1 is because of primary current I1, and the flux pi 2 is because of secondary current I2. These two are exactly opposite each other. Okay, so that means the resultant flux is called so that is pi naught. Okay, other pi r. Okay, this is always constant. The resultant flux is always constant, even though load is increasing or decreasing in the transformer. The resultant flux is always constant. That's why transformer is called as a constant flux device. Okay, so then only the transformer is working. If your winding is connected, if your winding is connected, same direction of the flux pi 1, there is no transformer action. Okay, so there is no transformer action if you are connecting the winding same direction of the flux pi 1. This flux pi 1, for example, this flux pi 1 direction is in this direction. If flux pi 2's direction is also in this direction, okay, so there is no opposition. There is no opposition. That's why there is no the current I1 is not increases. Current is not I1 is not increased. Because even though if you are connecting the load, the I1 is increasing because of there is no transformer action. If the pi 1 and pi 2 are both are an opposite, then only so the current I1 is increases and then the load demand. So to meet the load demand is possible. If the flux pi 1 and pi 2 are both are in exactly opposite, then only to satisfy the load, the some amount of current I1 exactly increases with the opposite to that of the flux pi 2. Okay, so then only the transformer action coming to picture. Otherwise, there is no transformer action. Okay, understood. That's why the transformer is called as a constant flux device. Okay, under loaded condition, so there is the information, and then these two magnetic fields oppose each other, resulting in a combined magnetic field of less magnetic strength than this single field produced by the primary winding alone when secondary circuit was open circuited. Okay, under open circuit condition, only one field is required, so that is called primary side. Okay, this combined magnetic field reduces the back EMF of the primary winding, causing the primary current I1 to increase slightly. Okay, so because of the current I1 is increases slightly. Primary current continues to increase until the core magnetic field is back at its original strength and for a transformer to operate correctly. Okay, this is the information about a balanced condition must always exist between the primary and secondary magnetic field. Thus, the result in a power, the result in power to be balanced and the same on both primary and secondary sides. That's why the transformer is called as a constant power device. So primary side and secondary side, the power is constant because of the transformer is a balanced system, balanced device. Okay, this is called primary side, primary winding. This is called secondary winding. So this is called transformer. So transformer does the some amount of current that is called I1 because of load I2, because of load this RL load. Okay, that may be inductive load. Okay, so secondary winding. So if you are connecting the load means compulsory draws the current from the supply. Compulsory draws the current from this source. The source is called as a transformer. So I2 is increases. Okay, if I2 is increases, flux pi 2 is increasing, and pi 2 is because of to start to nullify that the flux to reduce the flux. Exact opposition flux pi 1 is also increasing, and then exactly opposite to the pi 2, and then resultant flux is constant because of that pi 1. This I1 is also increasing to meet the load demand. That's okay. Understood. You can calculate the primary current IP by following methods. Primary current, this is called primary current, can be measured by using following methods. Understood. Horizontal component Ix is called I naught cos sin pi naught. You know well. horizontal. This is called a sine pi naught. This is called magnetizing component. This is called cos pi naught. Okay, horizontal component Ix is equal to I naught sine pi naught. So because of load, some amount of current is increases. That is called I1 dash. Okay, so I1 dash. That is angle called pi 2. Okay, that is called I1 sine pi 2. And vertical component Iy. This is called watt pull component. Under no load condition, I naught cos pi naught. Because of this load condition, so that's why I1 dash cos pi 2. So the resultant of these two is called I1 is equal to 100 of Ix square plus Iy square. So not square root of Ix square. So just I100 of Ix square plus Iy square. Then power factor is equal to cos pi, then Iy by Ix. Okay, try to consider here. This is the phase vector diagram of the practical transformer under loaded condition. Okay, so you know well under no load, you know well. So what is the relation between V1 and E1 here? V1 here, V1. Understood? Here V1. That means here compulsory. Here E1. This is called E1. And also it is also is equal to the E2. This also is equal to E2, no? So understood. So you know well under from the no load diagram, no load vector diagram of the transformer. Okay, practically and ideally both are same, exactly same. V1 and E1 are exactly phase opposition. Okay, that also equal to the V2. No? V2 and E2 are also exactly in phase. Okay, so V1 is equal to minus V2 and E1 is equal to E2 is equal to V2. Both are the E1, V2 and E2 are all are in phase, but V1 exactly phase opposition. Am I right? You know well according to phase. This is called magnetic flux pi. Okay, the flux pi, you know well. And this I naught is called because of no load current. That is called I naught magnetizing component and watt full component. No? So this is called magnetizing component, I mu. Am I right? This is called watt full component from the no load diagram, no load vector diagram of the. Okay. The resultant of these two is called I naught. Am I right? Resultant of these two, I mu and IW. The resultant of these two. It's called I naught. It's clear. The resultant of the IW plus and I mu is called I naught. So I naught is over. Up to here, same. Okay, up to no load current is same. So then, so what happened means, so if the load is connected here, the load is connected from the secondary side of the transformer. So because of that, some amount of current I2 draws from the supply. That current is called, okay, that current is called I2. So I2, so it is called inductive load, RL load. Okay, that's why, so across the inductor, current lags the voltage leads. Okay, current lags lagging condition and voltage leading condition. That's why some angle, so voltage leads. So if you are taking considering in this direction, vector direction, okay, so in this direction, the voltage leads and the current lags some angle pi 2, that is called load power factor angle pi 2. Voltage leads here, current lags, okay, some angle pi 2. You know well, from the transformer, I2 load current is proportional to the primary current. This current I2 is proportional to the primary current, but it's exactly opposition. You know well, exactly opposite. So that's why. So I2 amount of so what amount of current? So the magnitude, same amount of current produced because of load at another side, that is called I1 dash. This I1 dash because of load current. Understood? This I1 dash is because of load current. Understood? Up to here V1, V2, E1, E2 and I0 is same. Okay. But here I2 because of load extra, this is because of load. So load is connected. No? So that's why the power factor angle, load power factor angle pi 2. So current I2 lags the voltage by some angle, that is called pi 2. Okay, that's why we have to indicate like this manner in this load side. So when indicated like this means I2 is proportional, exactly proportional to the I1, but opposite direction. That's why. So I2 is in this direction means I1 exactly opposite direction, same amount of magnitude. Understood? That's why. So this the resultant of these two current, no load current and load current, is called actual current from the actual primary current. Okay, that is called I1. I1 is equal to I1 dash plus I naught. Understood? The resultant of these two is called actual current. So primary current, that is called I1. This is because of load. I1 dash cos pi 2 is because of load. So previous, this is because of only here up to here I naught. But because of load, this current is increases. So I naught sin pi naught, I naught cos pi naught is under no load condition. But because of loaded condition, so it is increases, magnetizing current is increasing, and watt pull component also increasing. It's clear. This called magnetizing component is increasing, and watt pull component is also increasing. So because of that, the actual primary current is, so it's called I1. So I1 is called actually primary current. It's clear. Under no load condition, what is the phasor diagram? Vector diagram. Under no load condition, this is the vector diagram. Okay, so here there is no I2. Here there is an I2 in practical under loaded condition. There is an I2 now here. I2 here taken into account under no load condition. Under loaded condition, some I2. But here under loaded condition, I2 is considered. But no load condition, there is no I2. Okay, so there is no concept of load current under no load condition. Under loaded conditions only, there is current I2 coming to picture. That is I2. So that's why. So we have to indicate I2 current. So exactly lags the secondary voltage by some angle. So that is called load power factor pi 2. Okay. Understood. So we know that the transfer ratio of the transformer states that total induced voltage in the each winding is proportional to the number of turns in the winding. Okay, the power output of the output and power input of the transformer equal volts times amperes. You know well V into I. Therefore, transformer ratio P1 P primary is equal to P secondary. You know well V1 I1 is equal to V2 I2. Then I2 is equal to V1 I1 by V2. V1 by V2 is equal to I2 by I1. But we know that voltage ratio is equal to the turns ratio. So N is equal to N1 by N2, V1 by V2, I2 by N. So this, information. Okay. So know that the current is inversely proportional to the both voltage and the number of turns. Current is inversely proportional to the both voltage and number of turns. The number of turns are increasing. Okay, so voltage is increasing. The number of turns are increasing, voltage is increasing, but current is decreasing. Okay, so that is the concept. So this is called the equivalent circuit of the transformer. Equivalent circuit diagram of the transformer.